All right, everyone, if you've survived the integration by parts videos, we're now going to learn about an integration method, which I think you'll find a lot simpler. So remember, in u substitution and integrated by parts, we needed to find these variables u in u substitution and in integration by parts u and dv. And there wasn't like a set in stone way we could figure out which ones those were. We kind of just had to for the most part in the beginning, sort of guess what they would be. But once you do some more problems, you get to see, you just recognize what you should use for them a little bit more and more. But for the most part, again, what I think people find difficult about those integrals is that there's no set in stone way to do every single one. There's no sequential process that if you follow it every single time, you'll be right. Because you have that when you got to choose the u or when you got to choose the u and the dv, and that kind of throws a monkey in the wrench of everything. But in partial fractions, while the method might seem a little bit more complicated mathematically, it's really not that bad once you get to work on it. And the great thing is there is a sequential way to do this one. You have a step-by-step A, B, C, D sort of procedure that you follow. And if you always follow it, you'll get the correct answer every single time. So in partial fractions, what we're looking for is if we have some function divided by another function. And in all these cases, the function that's going to be in the denominator is going to be some kind of polynomial or something we can break up into a bunch of factors. Now, generally, you're never going to have to go beyond a third order polynomial. And if it's a third order, it's actually really easy to factor. I'll even show you an example of one of those in this video. But for the most part, it's not going to be a whole lot of terms. But as you can see right down here, factoring is going to be really important. You're going to need to know how to factor, okay? So what we use in this method, and I don't know if you guys remember partial fractions from Algebra 2 or possibly pre-calculus, but it was something that's generally in those curriculums. We can take a quotient function that looks like this and actually split it up into a series of smaller quotients as long as we solve for these constants right here. Okay, and one thing you'll notice when we look in this kind of factored polynomial right here is in every single case we have this R1, R2, Rn, all that stuff. What those are called the roots. So for example, if we had x minus 2, R would be equal to 2. That's the root of that thing. That's what makes what's inside those parentheses 0. If we had x plus 2, R would be equal to negative 2 because negative 2 is what makes that thing 0. So when we have these R's down here, that's what we're saying. Those are what makes those inside of the parentheses equal to 0. Okay? So what we got to go over is a method for how we calculate what these constants, these A's as I wrote them here, we got to figure out how to calculate those things. And we do that by something called the Heaviside cover-up method. All right? And you see Heaviside cover-up method, I don't know, I think of like something someone would yell in a line of scrimmage in a football game or something, just be like, Blue 42, Heaviside cover-up 1, go! Or something like that. That's always what I imagine. Hopefully that wasn't too loud if you're listening to this in earbuds. But anyway, how we do that Heaviside cover-up method is to solve for these constants. We take basically that original quotient that we got, and what we do is we physically cover up with our hands the first, in this case if we're solving for A1, that first constant, we cover up that first parentheses or that first portion of the factor down below, and we plug in, notice that in everywhere there was originally an x, now there is the root of that first function, okay? So again, if we have a function that's like, let's say, 2x over x plus 2, x minus 3, in this case what we'll do is we will cover up the x plus 2 and we will plug in the root that makes that 0, which was x equals negative 2. So we will plug in x equals negative 2 for this x and this x, making sure we cover up that thing right here. Now, why do we do that? Well, because we covered up that one, when we plug in that root, we don't have this term in there anymore, so we won't get a 0 in the denominator, so everyone is happy, the world is amazing. So that's what we do, and we just do that for every single variable. So this is how we solve for that first constant right here, is we cover up that first term in the factor of the bottom, and we plug in the root that makes that factor 0 for everywhere in x, and that is how we evaluate that first constant. So to look back on a slide, remember what those constants are these guys right here, okay? They're the constants that go above those partial fractions, right? So again, now if we want to solve for the second constant, we cover up the second term and we plug in the root that makes that second term 0. Notice now in place of x everywhere, we have R2 instead of R1 before. So again, if we do the example we had before, if our function is 2x, x plus 2, x minus 3, what we'll do is we say, okay, the root of this second one is 3, x equals 3, so we cover up this term, just pretend it's not even there, and plug in x equals 3 everywhere we see an x, and we can therefore solve for this constant. So if we do that every single time, we will eventually find all of those constants, and we end up with an integral like this, which is much easier to solve because these integrals represent a constant, whatever that constant is, right up in here, multiplied by the natural log of whatever the denominator is, okay? We can use use substitution to prove that these integrals will be a natural log, or you can just trust me, they're always going to end up being a natural log integral. And so we basically just do all of them like that, and there we go. We got the solution to the integral. So we don't need to find any variables of u or dv in this case. Again, it's just very straightforward. I think a lot of students, the biggest problems they have is actually applying that Heaviside cover-up method. So if you need to, go back and rewatch the video, take notes on how to do the method, and when you're ready, you think you're ready to solve some example problems, go to the, or just, I guess, continue the video from this point. All right, so why don't you now, this is a fairly simple partial fractions integral. Why don't you try to solve this one using that Heaviside cover-up method we just talked about? Pause the video. Okay, so if you do this one, the first thing you want to do is, well, we got to find out what those factors in the denominator are. So let's rewrite this integral. If we factor it, it'll end up being x plus 2, times x minus 1. That's what our integral is, dx. So remember that if we convert this to a partial fraction solution, that's the same thing as saying this will be the integral of some constant a1 over x plus 2, and then plus some constant a2 over x minus 1 dx. Okay? So we got to use that Heaviside cover-up method to solve for a1 and a2. So in this case, a1 is going to be equal to, again, we're using this whole function up here to find this. We cover up the first term in that, basically pretend it doesn't exist. In this case, the root that makes that thing equal to 0 is x equals negative 2. So we plug x equals negative 2 into the rest of the equation, remembering to cover up or basically totally eliminate that term. So a1 would therefore be 1 over negative 2 plus 1. Okay, so if I remove this term, the only term I'm left with is this term right here. And when I plug in x equals negative 2, that's where that, I'm sorry, not plus 1, minus 1. God, that must have really confused some people. I apologize about that. So we have negative 2 minus 1. Okay? So what we're doing is we're plugging in the root that makes that first term 0 into that second one right there, which is why we get negative 2 minus 1. So therefore, the answer to this is very simple. A1 is equal to negative 1/3. Okay? So if you weren't able to get that, pause the video from this point and try to solve for what that constant a2 is and complete the rest of the integral. All right, so if you gave that a shot, using the same thing, we would say a2 is equal to 1 over, now in this case, we're going to be looking at, and let me erase some of this stuff because it's getting a little bit messy. So again, we have x plus 2, x minus 1. So the integral that we are trying, the constant we're trying to solve for, now we look at what makes this second one equal to 0, which is x equals 1. So again, Heaviside cover-up method, we cover up this thing, pretend it doesn't exist, and plug x equals 1 into what's left over. So if we do that, we will get 1 over 1 plus 2, or 1/3. Okay? So now if we plug this back into the original integral that we were trying to solve, now when I say that, I mean plug it back into this integral now that we found what a1 and a2 are equal to. If we do that now, we will end up getting the integral, or this is equal to the integral of a1, which is negative 1/3 over x plus 2, plus a2, which was 1/3 x minus 1 dx. And this is a pretty straightforward integral. This would just be negative 1/3 log, natural log of the absolute value of x plus 2 plus 1/3 natural log absolute value of x minus 1 plus c. So that's what that final solution looks like. And again, if you take the derivative of that solution, you'll get the original function that we were trying to take the integral of in the first place. Okay? So if you totally didn't get this, if you didn't get what was going on, go ahead, rewatch this portion of the video and try to solve it out again on your own. And if you have to, I would highly recommend writing down those rules for the Heaviside cover-up method, because it's a lot of steps and it's kind of hard to remember how to do everything just by watching the video and not actually writing the steps down. All right, so if you're ready to move on, let's try one that's a little bit more difficult. See if you can do this one. Now this one's going to be a little bit longer, but still, just give it a shot. Pause the video. Okay, so if we try this one again, the first thing we want to do is we want to factor that bottom. We want to get that into a set of factors. So this will be x plus 4 over, notice that every single term has an x. So one of the easiest factors is just pull an x out, and then this becomes x squared plus 3x minus 10. All right, now that becomes something a lot easier to factor. So this integral, therefore, becomes the integral of x plus 4 over x multiplied by x minus 2, then times x plus 5 dx. Okay, so if we do this now, we're going to have three constants, a1, a2, and a3, because we have three different terms that could all be 0 in the denominator. So this integral will be the integral of a1 over x plus a2 over x minus 2 plus a3 over x plus 5 dx. Okay, so if you weren't able to get to this stage, go ahead, pause the video, try to solve it from this point out, find that a1, a2, and a3, and eventually figure out how to solve this integral. All right, so remember, if we want to solve this integral, we got to do this Heaviside cover-up method. So if we want to find a1, remember what we do is we cover up this first term, pretend it doesn't exist. What x value makes that first term 0? Well, it's x is equal to 0. So what we want to do is we want to plug in x is equal to 0 into this fraction with that first x term covered up like it doesn't exist, and go ahead and solve it from there. So that's going to end up being on the top 0 plus 4 over on the bottom. Remember, we cover up this first term, we pretend it doesn't exist, 0 minus 2 times 0 plus 5. All right, if we end up doing that, what do we get? We end up getting negative 2/5. Okay? So again, I really want you guys to work on these your own. Don't just passively watch the video. Do this yourself. If you weren't able to get to this point, pause the video and try to solve for a2 and a3 and solve the integral from this point on. Okay? So if you've attempted to solve this integral, if we go through and solve for a2, again in a2 we're going to be looking to cover up this term down here, and let me scroll up a little bit so we can see this. But we want to cover up that second term. Recall what makes that second term 0. Well, it's x is equal to 2. So we want to cover up that one term, and then we want to evaluate this entire fraction with that term missing and plugging in x equals 0, the x value that makes that term equal to 0. So if we do that, we'll end up getting 2 plus 4 over 2 times 2 plus 5. Okay? Remember, it's called the cover-up method because we cover up this second term. If we didn't cover that up and we plugged in x equals 2, we would get 0 in the denominator, bad news bears, nothing would be able to happen. Okay? So if we plug this in and solve for that, we will end up getting, let's see, this will give us 3/7. Okay, interesting fraction right there. So now if we go ahead and solve for a3, we're going to want to plug in the value that makes the third term equal to 0. So that will be x is -5. We are going to cover up that third term and plug x equals -5 into all the x values into that quotient term right there. So if we go ahead and do that and solve for a3, we get a3 is -5 plus 4 divided by -5 times -5 minus 2. And if we go ahead and do that, we will get, this one will be a little bit trickier. It's -1/35. All right, cool. Okay, so now we got all of our values for a. So if we plug this into the integral we're actually solving is going to be -2/5x. Actually, let me write that another way just because some people might be like, wait, how did the 5 get down there? Remember that first a value is -2/5. So we'll have -2/5/x plus 3/7 x minus 2. Then we'll have -1/35 x plus 5 dx. And again, it just turns into an integral that's just, the solution is a bunch of log terms. So if we go ahead and solve this, we'll end up getting -2/5 natural log of the absolute value of x plus 3/7 natural log of the absolute value of x minus 2 minus 1/35 the natural log of the absolute value of x plus 5 plus c. Okay, so again, yeah, we're getting into more mathematically dense methods of integration. This is also, remember, I told you guys at the beginning of the semester, integration's harder than taking derivatives, okay? It's not nearly as straightforward as the chain rule or the product rule and stuff like that. So I highly recommend, if you're having trouble with some of this stuff, rewatching the videos is the best way to understand how they're done. After that, though, come into class, meet me during tutorial, come see me during a free period. I'm 3rd, blue block, or 6th, or after school, you know, if you make an appointment with me, and we'll try to work out doing some of this. But also understand you guys got a textbook on you, and that textbook has tons of these problems inside there that you can use for practice. So don't overlook that textbook as a really valuable resource to help you understand some of this stuff. So I will see you guys in class later.